Right now, you could have access to a perfect rocket, flawless engines, unbreakable materials, limitless precision, and you would still be stranded in your own solar system. The nearest star, Proxima Centauri, sits just over 4 light-years away, and even perfection cannot close that gap. By the end of this breakdown, you'll understand exactly which barriers physics has locked into place and why none of them disappear when we make our rockets better. If this is the kind of science you like, subscribe for more breakdowns like this. Let's break it down, step by step. Imagine someone hands you the ultimate spacecraft. The engines convert fuel to thrust with perfect efficiency, not a single joule wasted. The structure never cracks, never buckles, never overheats. The guidance system points wherever you command, instantly, flawlessly. You have solved every engineering problem we currently struggle with. You aim this miracle machine at Proxima Centauri, fire the engines, and wait. And you realize you are still not going anywhere near fast enough. And even if you were, you could not carry enough fuel to stop when you arrived. This is the perfect rocket paradox. The problem is not that our rockets are poorly built. The problem is that the mission itself demands things physics will not allow. No matter how well we build, we are going to walk through 7 hard barriers: energy, the rocket equation, braking, relativity, the interstellar medium, navigation, and time itself, measured in decades of unforgiving exposure. Each one is a wall. Together they form a cage. Every solution to one barrier makes another barrier worse. The result is not that interstellar travel violates the laws of physics. It is that it obeys them so ruthlessly that practical missions collapse under their own requirements. Notice what that means. The nearest star is not a destination problem. It is a physics problem. We are going to translate each barrier into something simple, what you would have to pay. Not in money, but in mass, energy, time, and risk. By the time we reach the end, you will see why perfect rockets is not enough and what it would actually take to change the answer. Here is the method. For each barrier, we identify the constraint, trace its consequences, examine the alternatives, and ask what remains impossible even after we fix everything fixable. Keep that structure in mind. It will keep us honest. The stakes are higher than one mission. If the nearest star is unreachable with perfect technology, then the question extends outward. Are we alone? Not because no one else exists, but because the space between stars is a filter. No civilization crosses easily. That is where this leads. But first, we need to know exactly how far nearest really is. Proxima Centauri sits 4.24 light-years away. That number gets quoted often enough that it loses meaning. Let us rebuild your intuition from the ground up, step by step, using distance scales you already understand. Start with Earth. The circumference is roughly 40,000 kilometers. You could walk that distance in about a year if you never stopped. Now zoom out. The Moon orbits at 384,000 kilometers, about 10 times Earth's circumference. The Sun sits 150 million kilometers away, which we call 1 astronomical unit. Light from the Sun takes 8 minutes and 20 seconds to reach us. You are already far outside walking scale. Keep zooming. Neptune, the outermost planet, orbits 30 astronomical units out, 4.5 billion kilometers from the Sun. Voyager 1, humanity's most distant spacecraft, has traveled about 24 billion kilometers and is currently moving at roughly 17 kilometers per second relative to the Sun. It has been flying for nearly 5 decades. It has not yet left the Sun's true sphere of influence. Look at this. Voyager 1 will not reach the distance of Proxima Centauri for another 73,000 years at its current speed. That is not a rocket problem. That is a distance category problem. The gap between our solar system and the nearest star is not a longer trip. It is a different kind of space. Now zoom out again. The Oort cloud, a shell of icy bodies surrounding the Sun, may extend out to 100,000 astronomical units, roughly 2 light-years. Proxima Centauri sits just beyond that, at about 270,000 astronomical units. Imagine the entire Oort cloud as a single pixel on your screen. Proxima Centauri would sit 2 pixels away. The space between stars is not empty corridor. It is gulf. Here is an analogy that makes the scale feel real. If the Sun were a grain of sand in New York City, Proxima Centauri would be another grain of sand in Los Angeles. Everything in between, thousands of kilometers of emptiness, is interstellar space. Notice what changes when you think in those terms. The problem begins with speed. To cover 4.24 light years in a human lifetime, say 50 years, you need to travel at about 8.5% the speed of light. That is roughly 25,000 kilometers per second. Voyager 1 moves at 17 kilometers per second. You need to go more than 1,400 times faster than the fastest object humanity has ever built. Here's the question. What does it cost to go that fast? And what does it cost to stop once you get there? We need to be precise about what impossible means because the word gets misused. Physical impossibility means the laws of physics forbid it outright. Traveling faster than light, for example, or creating energy from nothing. Practical impossibility means the laws of physics allow it in principle, but the resource requirements, risks, or time scales make it unrealistic for any civilization remotely like ours. Interstellar travel sits in the second category. Physics does not forbid a probe from reaching Proxima Centauri. Physics forbids it from reaching Proxima Centauri quickly, safely, with useful payload, and with the ability to stop and send back data, all at once, using anything close to our current or foreseeable industrial capacity. That distinction matters. Let us define the mission types clearly because reaching Proxima Centauri can mean different things. A flyby mission accelerates coasts and passes through the target system at high speed without stopping. It gets one brief window to gather data as it screams past. A rendezvous mission accelerates, coasts, then decelerates to match the target's velocity, allowing extended observation and communication. A crewed mission adds life support, radiation shielding, redundancy, and habitable volume, massively increasing payload. A generational mission stretches the timeline across multiple human lifetimes, lowering speed requirements but introducing biological and social sustainability problems. Each type faces different barriers. The hardest is rendezvous, because it demands the fuel budget to accelerate and decelerate. That is the standard we will use here. Why focus on rendezvous? Because a flyby is not reaching in any meaningful sense. You spend decades getting there for a few hours of data as you zip past at 25,000 kilometers per second, unable to stop, unable to orbit, unable to explore. The science return is thin. The mission justification is weak. If we are going to travel between stars, we need to be able to stay. That is the mission profile that reveals the true barriers. Keep that in mind. When we say impossible, we mean impossible to stop, observe, and communicate results in a realistic time frame with realistic resources. Here is the constraint we will trace. Energy is the currency of speed. The rocket equation is the tax collector. Braking doubles the bill. Relativity sets the speed limit. The interstellar medium punishes high speed. Navigation demands precision, and time kills machines. Together, these constraints do not add. They multiply. You cannot optimize your way around multiplication. You can only change the terms. So, what would it take to change the terms? Speed costs energy, and the cost curve is not linear. It is quadratic. Kinetic energy equals 1/2 mass times velocity squared. That squared term is the killer. If you want to go twice as fast, you need 4 times the energy. 3 times as fast, 9 times the energy. 10 times as fast, 100 times the energy. This is not an engineering problem. This is mathematics, and mathematics does not negotiate. Look at this. To accelerate 1 kilogram to 8.5% light speed, the speed we need for a 50-year crossing, requires about 3.2 times 10 to the 14th joules of kinetic energy. That is the energy in roughly 7.6 thousand tons of TNT for 1 kilogram. Your spacecraft is not 1 kilogram. Let us translate that into infrastructure. A large nuclear power plant generates about 1 gigawatt, or 10 to the 9th watts. Running that plant continuously for 1 year produces about 3.2 times 10 to the 16th joules. To accelerate a 1-ton spacecraft, 1,000 kilograms, which is tiny for interstellar missions, to 8.5% light speed requires 3.2 times 10 to the 17th joules. That is roughly 10 years of output from a gigawatt power plant, assuming perfect conversion of electrical energy into kinetic energy. No losses, no inefficiency. Perfect. And that is just for 1 ton, just for acceleration, just to get moving. You have not stopped yet. You have not powered instruments. You have not shielded anything. Notice what happens when the mass grows. A more realistic probe might mass 10 tons. Now you need 100 years of gigawatt plant output. A crewed mission might require hundreds of tons. Life support, habitation, redundancy, shielding. The energy budget explodes into centuries or millennia of industrial-scale power generation, all front-loaded into the mission. Here is the reframe. Perfect rockets does not mean free energy. It means perfect efficiency in converting available energy into thrust. But the energy still has to come from somewhere. You still have to generate it, store it, or carry it as fuel. Every joule of kinetic energy you want must be paid for, either as fuel mass or as external energy input. The universe does not offer discounts. Now add the second-order problem. Where does that energy come from? If you carry it as chemical fuel, you are bound by chemical energy density, roughly 10 to the 7th joules per kilogram for the best chemical propellants. If you carry it as nuclear fuel, you gain 2 orders of magnitude, 10 to the 9th joules per kilogram for fission, potentially 10 to the 14th for fusion. If you could carry antimatter, you approach 10 to the 17th joules per kilogram, the theoretical maximum from matter energy conversion. But antimatter does not exist in bulk. Fusion is not yet controlled reliably. Even fission fuel must be converted into thrust, and conversion always involves inefficiency unless you assume perfection. So let us assume perfection and see where it leads. Perfect efficiency means every joule of fuel energy becomes kinetic energy. No waste heat, no radiation losses, no incomplete combustion. You are still bound by how much fuel you can carry because fuel has mass, and mass resists acceleration. This is where the energy barrier intersects the next barrier, the rocket equation. Energy tells you what you need. The rocket equation tells you what you must pay to get it, and the price is exponential. Here is the core problem. Rockets work by throwing mass backward. Conservation of momentum forces the rocket forward. To go faster, you throw more mass backward, or you throw it harder, or both. But here is the trap. The mass you throw is mass you must carry. The more you need to throw, the heavier you are at the start, which means you need even more fuel to accelerate that heavier starting mass. This feedback loop is the rocket equation, and it is exponential. Let me show you what that means. Without algebra first, then we will touch the formula briefly for those who want it. Imagine you want to double your speed. You burn fuel and throw exhaust backward. But the fuel you need for the second half of the burn is fuel you had to carry during the first half, which means you needed extra fuel just to accelerate that fuel. The result? Your fuel requirements grow faster than your speed requirements. For small speed changes, this is manageable. For interstellar delta V, the total velocity change needed, it becomes absurd. The ratio between your starting mass and your final mass grows exponentially with the speed change you want, divided by your exhaust velocity. That ratio is called the mass ratio. If your mass ratio is 10, you need 10 kilograms of rocket at the start to deliver 1 kilogram at the end. If your mass ratio is 100, you need 100 kilograms to deliver 1 kilogram. Notice what happens when the ratio climbs into the thousands. The rocket equation is delta V equals exhaust velocity times the natural logarithm of the mass ratio. Delta V is the total speed change you need. Exhaust velocity is how fast you throw the propellant backward. It measures your engine's efficiency. The mass ratio is initial mass divided by final mass. Let us plug in real numbers. Say you want delta V of 25,000 kilometers per second for a one-way trip, and your exhaust velocity is 50 kilometers per second, which is optimistic for chemical rockets but realistic for ion drives or advanced concepts. The mass ratio is E to the power of delta V over exhaust velocity. That is e to the power of 500. The exponential function of 500 is a number so large it has no physical meaning. You would need more mass than exists in the observable universe to deliver a 1 kilogram payload. This is not an exaggeration. This is arithmetic. So, how do you escape? you increase exhaust velocity. Chemical rockets top out around 4.5 kilometers per second. Ion drives reach 50 to 100 kilometers per second. Theoretical fusion drives might reach 1% the speed of light, 3,000 kilometers per second. Let us recalculate with fusion exhaust velocity. Delta V of 25,000 kilometers per second divided by 3,000 kilometers per second gives a mass ratio of e to the power of 8.3, which is roughly 4,000. To deliver 1 ton of payload, you need 4,000 tons at launch. That is the entire mass of the spacecraft: structure, fuel, engines, payload, sitting on the launch pad. For a crewed mission with life support, the payload might be 100 tons. Now you need 400,000 tons. For a one-way trip, you have not stopped yet. Staging helps for Earth-to-orbit launches, where you drop empty fuel tanks and engines as you climb. But interstellar missions do not have multiple stages in the traditional sense. You are crossing a void with no refueling stations, no places to discard mass, no infrastructure. You could stage by dropping empty fuel tanks as you go, but you still carried those tanks during the early burn, so the mass penalty already happened. The exponential nature of the rocket equation punishes every kilogram you add, no matter when you drop it. Here is the reframe. High exhaust velocity helps, but it does not remove the exponential character. It shifts the curve. It does not flatten it. What would flatten it? Not carrying your fuel. We will return to that idea later. For now, let us make the problem worse. Everything we have discussed so far assumes you are content to fly past Proxima Centauri at 25,000 kilometers per second, unable to stop, unable to orbit, gathering data for a few hours before vanishing into the interstellar dark. That is a flyby. A rendezvous mission demands something far harder. You must slow down, and slowing down costs exactly as much as speeding up in terms of delta V. If you accelerated to 25,000 kilometers per second, you must decelerate by 25,000 kilometers per second to match Proxima's velocity and enter orbit. The rocket equation applies twice. Your mass ratio is now squared. Look at this. If your one-way mass ratio was 4,000 with fusion exhaust velocity, your two-way mass ratio is 4,000 squared, which is 16 million. To deliver 1 ton of payload into orbit around Proxima Centauri, you need 16 million tons at launch. For comparison, the International Space Station masses about 420 tons. The Saturn V rocket at launch massed about 3,000 tons. You are talking about a vehicle 5,000 times heavier than the Saturn V, just to deliver 1 ton. A crewed mission with 100 tons of payload would require 1.6 billion tons at launch. That is more mass than humanity has ever launched into space in all of history, for a single mission. This is the braking problem. Stopping doubles the fuel budget, and the fuel budget was already exponential. Can you brake without propellant? In principle, yes. In practice, the options are limited. Atmospheric braking works at planets with thick atmospheres. You skim the upper atmosphere and convert kinetic energy into heat, slowing down without spending fuel. But Proxima Centauri b, the closest known exoplanet in the system, is a rocky world with unknown atmospheric properties, and even if it has atmosphere, you would need heat shielding capable of surviving entry at interstellar speeds, which creates shockwave heating far beyond anything we have tested. More importantly, you cannot assume a useful atmosphere exists. The mission must work without it. Look at another option: magnetic or plasma sails that interact with the interstellar medium. You deploy a large electromagnetic field or a cloud of charged particles ahead of the spacecraft, and drag against the sparse interstellar plasma slows you down over time. This trades propellant for time and structure size. The magnetic field must be enormous, potentially hundreds of kilometers across, to generate meaningful drag. That field requires power, superconducting coils, and structural mass. The time required to brake stretches the mission duration, increasing exposure to radiation and component failure. Notice the trade-off. You remove propellant mass, but add structure mass and time risk. Another braking concept: stellar wind braking. The target star emits a stream of charged particles. It's stellar wind. You deploy a magnetic sail and let the stellar wind push against it, gradually slowing the spacecraft as you approach. This works in theory, but requires enormous sail structures and only becomes effective very close to the star, meaning you spend most of the approach coasting at high speed and only brake in the final phase. The braking time might span years, during which navigation must be precise and the sail must remain intact. Gravitational assists could help, swinging around Proxima to shed velocity. But Proxima is a small red dwarf with weak gravity compared to the Sun, and useful flybys depend on having other massive bodies in the system positioned correctly. When you arrive, you cannot count on it. Here is the practical catch. Every braking method that does not use propellant requires massive structures, long timescales, or both. Massive structures worsen the rocket equation on the way out because you must accelerate that structure to interstellar speeds. Long timescales worsen reliability because more time means more exposure to failure modes. Propulsive braking is straightforward, but fuel-hungry. Non-propulsive braking is fuel-efficient, but structure-hungry and time-hungry. You are choosing which constraint to sacrifice to. And we have not yet discussed what happens when you try to go faster. The speed of light is not a suggestion. It is a hard boundary, and the closer you approach it, the harder every additional increment becomes. At low speeds, below 1% light speed, relativity barely matters. Newtonian mechanics gives accurate predictions, but as you push past 10%, 20%, 30% light speed, relativistic effects dominate. Your mass, from the perspective of an outside observer, increases. The energy required to accelerate further grows without bound. You cannot just keep accelerating until you hit light speed, because the universe forbids it. Here is what that means for interstellar missions. The faster you want to go, the more brutally the rocket equation punishes you, even with perfect engines. Let us trace the numbers. Classical kinetic energy is 1/2 mass times velocity squared. At 8.5% light speed, that formula is still reasonably accurate. At 50% light speed, relativistic corrections become significant. The correct formula involves the Lorentz factor, gamma, which equals 1 divided by the square root of 1 minus velocity squared over the speed of light squared. At 50% light speed, gamma is about 1.15. Your effective mass is 15% higher than your rest mass, and the energy required to reach that speed is 15% more than the classical formula predicts. Not catastrophic, but noticeable. At 90% light speed, gamma jumps to about 2.3. Your effective mass more than doubles. At 99% light speed, gamma is about 7. At 99.9%, gamma is about 22. Notice the curve. Every extra slice of speed costs disproportionately more. Time dilation helps the onboard experience. If you accelerate to 90% light speed, time aboard the spacecraft runs slower relative to Earth. A journey that takes 47 years for Earth observers might feel like only 20 years to the crew. This is real, measurable, and confirmed by every particle accelerator and GPS satellite in operation. But time dilation does not reduce the energy cost. It does not reduce the fuel mass. It does not reduce the radiation dose accumulated over the journey. It only compresses the subjective experience for those aboard. For mission planners on Earth, the energy and mass budgets remain unchanged. The probe still needs the same propellant. The industrial output required to build and fuel it remains the same. Time dilation is a psychological benefit, not a physical loophole. Relativity also tightens the other barriers. High-speed collisions with interstellar dust become more energetic due to relativistic momentum. Shielding requirements grow. Communication redshift becomes significant. Signals transmitted from a spacecraft moving at high fractions of light speed are Doppler shifted, requiring receivers on Earth to account for frequency changes. Navigation becomes more complex because relativistic velocity addition does not follow simple arithmetic. But the core problem is energy. The closer you push toward light speed, the more energy each additional increment demands, and that energy must come from fuel mass or external beaming, both of which slam into the rocket equation. Here's the reframe. Relativity is not the only barrier, but it hardens every other one. It is the endgame wall. Would going slower help? Yes, absolutely. If you accept longer mission durations, you can fly at lower speeds, reduce energy requirements, and ease the rocket equation. A mission at 1% light speed would take over 400 years to reach Proxima Centauri, but would require far less fuel than a 50-year mission. This opens the door to generational ships, where multiple human generations live and die aboard the vessel. But now, you have traded speed problems for biological and social problems, maintaining a closed-loop ecosystem for centuries, preventing genetic bottlenecks, ensuring social stability across generations, and keeping technology functional over timescales longer than any machine has ever operated. Notice the trade-off. You do not escape impossibility, you just shift which kind of impossibility you face, and none of this helps if the interstellar medium shreds your ship before you arrive. Interstellar space is not empty. It contains gas and dust, hydrogen, helium, trace heavier elements, tiny grains of silicate and carbon. The density is astonishingly low, roughly 1 atom per cubic centimeter in typical regions, far thinner than the best vacuum we can create in a laboratory. But at interstellar speeds, even single atoms become bullets. Let us calculate the impact energy. A hydrogen atom has a mass of about 1.67 times 10 to the negative 27 kilograms. At 8.5% light speed, 25,000 kilometers per second, the kinetic energy of that single atom relative to your spacecraft is about 5 times 10 to the negative 13 joules. That is a tiny number, but compare it to the atom's rest mass energy, which is about 1.5 times 10 to the negative 10 joules. The kinetic energy is about 0.3% of the rest mass energy. Not relativistic yet, but significant. Now, scale up. Your spacecraft sweeps through space, colliding with roughly 1 atom per cubic centimeter. If your cross-sectional area is 10 square meters, a modest spacecraft, you encounter about 2.5 times 10 to the 14 atoms per second at that speed. Multiply by the energy per atom, and you are absorbing about 125 watts of continuous impact energy. That is manageable. But interstellar space also contains dust grains. These are rare, maybe 1 grain per cubic kilometer, but far more massive than atoms. A dust grain 1 micrometer in diameter, composed of silicate, mass is about 2 times 10 to the negative 15 kilograms. At 8.5% light speed, that grain carries about 6 joules of kinetic energy. 6 joules is the energy of a bullet fired from a handgun. 1 dust grain, hitting your spacecraft at interstellar speeds. How do you protect against that? Passive shielding is the simplest approach. The Whipple shield, developed for spacecraft in Earth orbit, uses multiple layers of material spaced apart. The first layer vaporizes the incoming particle into a cloud of smaller fragments. Subsequent layers absorb the dispersed energy. This works for micrometeoroids in orbit, where impact speeds are around 10 kilometers per second. At interstellar speeds, the physics change. The impact energy is higher by a factor of thousands. The shielding must be thicker, heavier, and more complex. And thick shielding means more mass, which worsens the rocket equation, which demands more fuel, which makes you heavier, which requires even more shielding. Look at this feedback loop. Shielding protects you, but carrying shielding makes the mission harder. Could you use a sacrificial forward shield? Yes. Imagine deploying a cloud of particles or a thin sheet of material ahead of the spacecraft, far enough forward that when dust grains hit it, the resulting debris cloud disperses before reaching the main vehicle. You're using disposable mass to absorb impacts, but that sacrificial mass must be accelerated along with the spacecraft, adding to the initial mass budget. Alternatively, you could use a magnetic or electrostatic shield, generating a strong field ahead of the spacecraft to deflect charged particles. This works for ions, hydrogen nuclei, helium, cosmic rays, but not for neutral dust grains. Dust grains have no net charge and pass through magnetic fields unaffected. You still need physical shielding for dust. The magnetic field helps with radiation, but does not solve the dust problem. Another concept. Deploy a plasma cloud ahead of the spacecraft. The plasma intercepts incoming particles and vaporizes them before they reach the ship. This requires power to generate and maintain the plasma, structural mass to hold the plasma generators, and careful field geometry to keep the plasma in place while moving at high speed. Every solution demands more mass, more power, or more complexity. Notice what this means. The interstellar medium is not just a hazard, it is a mass tax. Every ton of shielding you add must be accelerated and decelerated, doubling the fuel cost due to the braking requirement. The rocket equation multiplies that cost exponentially. A 10% increase in shielding mass might require a 50% increase in fuel mass, depending on your exhaust velocity and delta V. Here is the deeper problem. We do not know the interstellar medium between here and Proxima Centauri in detail. We have measurements of the local medium around the Sun, and we have models of the galactic distribution. But specific densities, grain size distributions, and ionization states along a particular trajectory are uncertain. You must design for worst-case scenarios, which means over-engineering the shielding, which makes the mass problem worse. You are building a mission profile around incomplete data, knowing that any underestimate could result in mission failure halfway through a multi-decade journey. What does that imply for navigation? Hitting a star sounds easy. Stars are huge. Proxima Centauri has a radius of about 100,000 kilometers, roughly 14% the radius of the Sun. But you are not trying to hit the star. You are trying to enter orbit around a planet or achieve a specific trajectory through the system, and planets are tiny. Proxima Centauri b, the closest exoplanet in the system, has a radius similar to Earth, roughly 6,400 kilometers. From 4 light-years away, that planet subtends an angle of about 0.000003 degrees. A tiny pointing error at launch grows into a huge miss at arrival. Let us quantify that. If your initial trajectory is off by 1/1,000,000th of a radian, a tiny angle, after traveling 4.2 light-years, you miss your target by about 4 billion kilometers. That is the distance from the Sun to Neptune, 1/1,000,000th of a radian. Proxima Centauri is moving, relative to the Sun, at about 22 kilometers per second. The Sun is moving relative to the local galactic frame. Your spacecraft is moving relative to all of them. The trajectory must be calculated not for where Proxima is now, but where it will be when you arrive, decades or centuries in the future. Stellar motion is well measured, but small uncertainties in position and velocity compound over time. A 1% error in Proxima's velocity estimate translates into a 4 light-day position error after a 50-year flight. That is about 346 times the Earth-Moon distance. You must know the target's motion with extraordinary precision and update your trajectory as new measurements refine the estimate. But mid-course corrections cost propellant. Every trajectory correction requires thrust. You fire engines to adjust your velocity vector, aligning it with the updated target position. But fuel is limited, and every kilogram of fuel spent on corrections is 1 kilogram not available for acceleration or braking. Mission planners must balance early precision, which requires better instruments and more computational power, against the fuel reserve needed for corrections. Autonomous navigation becomes essential. Light-speed communication delay means you cannot joystick the spacecraft from Earth. A signal takes 4.2 years to travel each way. By the time you see a problem and send a correction, the spacecraft has drifted for over 8 years. It must diagnose pointing errors, calculate corrections, and execute burns without human intervention. Arrival geometry adds another layer. If you are attempting a rendezvous, you must match not just position, but velocity. Proxima Centauri b orbits its star every 11.2 days at a distance of about 0.05 astronomical units, 7.5 million kilometers. That is very close, well inside Mercury's orbit around the Sun. The planet's orbital velocity is roughly 140 kilometers per second. Your spacecraft approaches at 25,000 kilometers per second in the frame of the solar system. But Proxima's motion and the planet's orbital velocity mean your relative velocity could be different. You must time your arrival to intercept the planet at the correct point in its orbit, then execute a braking burn with precise timing and orientation. Notice the compounding requirements. You need accurate knowledge of the star's position and motion, the planet's orbital parameters, the spacecraft's trajectory, and the remaining fuel mass and engine performance. Pointing precision for braking is even tighter than for trajectory correction. If your braking burn is misaligned by 1 degree, a significant fraction of your thrust is wasted in the wrong direction, and you may not shed enough velocity to capture into orbit. You enter the system too fast, swing past, and continue into interstellar space with no fuel left to correct. Mission failure. The navigation problem is not separate from the other barriers. It feeds into them. High pointing precision requires better sensors, which require mass and power. Mid-course corrections require fuel reserves, which increase the initial mass budget. Autonomous systems require redundancy and fault tolerance, which add complexity and more mass. Every requirement reinforces the others. And all of this assumes the spacecraft survives the journey intact. Machines break. The longest operating spacecraft humanity has built, Voyager 1 and 2, have been flying for nearly 50 years, but they are beginning to fail. Power output from their radioisotope thermoelectric generators has declined. Several instruments have shut down due to insufficient power. One of Voyager 2's thrusters degraded, requiring a switch to a backup set. These probes were built with 1970s technology and designed for multi-decade operation, yet they are barely holding on. A mission to Proxima Centauri, traveling at higher speeds with more complex systems, must function for 50 to 400 years depending on speed, with no possibility of repair. That is not an engineering challenge. That is a statistical near impossibility. Components degrade. Radiation from cosmic rays damages electronics, flipping bits in memory, inducing errors in logic circuits, and gradually degrading semiconductor materials. Shielding helps but adds mass. Redundancy helps. You carry multiple copies of critical systems and switch to backups when primaries fail. But redundancy also adds mass, and every backup system is also aging in parallel, exposed to the same radiation environment. Thermal cycling stresses materials. In interstellar space, one side of the spacecraft faces the sun or the target star, absorbing heat. The opposite side radiates into the cosmic microwave background at roughly 3 degrees Kelvin. The temperature gradient induces expansion and contraction, fatiguing materials over millions of cycles. Welds crack, solder joints fail, seals leak. Notice the timescale. 50 years is roughly 440,000 hours. Electronic components rated for 100,000 hours are considered long life. You need components that last 5 times longer, or you need enough redundancy to replace them multiple times over. Power systems over decades face degradation. Solar panels degrade from radiation exposure, losing efficiency over time. Radioisotope generators decay predictably. Half-life determines power decline, but they also suffer from thermoelectric material degradation. A probe leaving the solar system loses solar power entirely once it moves beyond a few astronomical units. It must rely on onboard power. Radioisotopes, potentially nuclear fission reactors, or theoretical fusion reactors if those become viable. Each option has failure modes. Radioisotope generators lose power steadily. Fission reactors require coolant systems, control mechanisms, and shielding, all of which add mass and complexity. Fusion reactors are not yet demonstrated. You are choosing between proven but limited power sources and unproven but powerful ones. What does that say about mission risk? Autonomy is mandatory, but fragile. The spacecraft must monitor its own health, detect failures, switch to backups, adjust trajectories, manage power budgets, and execute the mission plan without human oversight. Software bugs that lay dormant for years can trigger at critical moments. Hardware faults can cascade. One failed sensor feeds bad data to the navigation system, which fires thrusters incorrectly, wasting fuel and misaligning the spacecraft. You need fault-tolerant software, which means extensive testing, but you cannot test 50-year operation on the ground. You can accelerate some tests, thermal cycling, radiation exposure, but you cannot simulate decades of space environment interaction in weeks. You are extrapolating from incomplete data. The probability of at least one critical failure over 50 years, given hundreds of components each with small individual failure rates, approaches certainty. You must design for failure and still expect mission loss. Micrometeoroids and dust, already discussed as high-speed hazards, also contribute to slow degradation. Small impacts pit surfaces, degrade coatings, and puncture thin structures. Over decades, cumulative damage adds up. Solar arrays lose efficiency as dust and pits scatter light. Optical instruments, cameras, spectrometers develop blind spots. Communication antennas lose gain as surface roughness increases. Each degradation mode is small, but they stack. What starts as a robust spacecraft becomes a fragile, limping vehicle by the time it reaches the target, and if it cannot communicate, the mission is worthless. You have reached Proxima Centauri. You have survived the journey, navigated precisely, braked into orbit, and begun collecting data. Now you must send that data home. The light speed delay is 4.2 years each way. Any signal you transmit takes 4.2 years to reach Earth. Any command Earth sends takes 4.2 years to arrive. You are operating on an 8.4-year round-trip communication loop. Real-time control is impossible. But the delay is only part of the problem. The bigger issue is power and signal strength. Radio signals spread as they travel, following an inverse square law. A signal transmitted from Proxima Centauri reaches Earth diminished by a factor proportional to the square of the distance. 4.2 light-years is roughly 4 times 10 to the 16th meters. The signal spreads over a sphere of that radius. The intensity drops by a factor of roughly 1.6 times 10 to the 33. Your spacecraft has limited power. A small probe might have a few hundred watts available for communication. A large crewed ship might have kilowatts. Compare that to the Voyager probes, which transmit at roughly 23 watts and are currently over 24 billion kilometers from Earth, about 0.0025 light-years. Their signals are barely detectable with Earth's largest radio telescopes. Proxima Centauri is about 1,700 times farther away. The signal is weaker by a factor of 1,700 squared, roughly 3 million. To achieve the same received signal strength as Voyager, you would need 3 million times the transmit power, roughly 70 megawatts just for communication. That is more power than the entire spacecraft has available. You cannot afford it. So, you use larger antennas and focus the beam. Antenna gain concentrates the signal into a narrow cone, increasing intensity in the direction of Earth while reducing it elsewhere. A large dish antenna, say 10 meters in diameter, can provide significant gain at radio frequencies. But beam width narrows as gain increases. A high-gain antenna might have a beam width of a fraction of a degree. You must point it at Earth with extreme precision. Earth is moving in its orbit around the Sun. The Sun is moving through the galaxy. The spacecraft is moving, potentially in orbit around Proxima. The pointing must track Earth's position continuously, requiring accurate ephemerides, tables of Earth's motion, loaded into the spacecraft's navigation system before launch and updated if possible. A pointing error of 1 degree means the beam misses Earth entirely, and the signal is lost. Data rate is another constraint. Communication bandwidth depends on signal strength and noise. The received signal strength at Earth, even with high-gain antennas on both ends, is extremely weak. Background noise from the cosmic microwave background, galactic radio sources, and Earth's own interference limits how faint a signal can be detected. The result: data rates are measured in bits per second or tens of bits per second, not megabits. Transmitting a single high-resolution image, say 10 megabytes, might take weeks or months. Transmitting the full data set from a multi-year orbital science mission could take decades. By the time the data arrives on Earth, the scientists who planned the mission may have retired or died. Notice the disconnect. The mission duration, the communication delay, and the data transmission time all compound, stretching the project across multiple human generations. Could you use laser communication instead of radio? Yes, in principle. Lasers offer much higher data rates and more focused beams. But lasers require precise optical pointing, are affected by interstellar dust scattering, and demand even tighter alignment than radio. A laser beam from Proxima Centauri would diverge due to diffraction, and even a well-focused beam spreads to thousands of kilometers diameter by the time it reaches Earth. You need large receiver telescopes on Earth and onboard the spacecraft, adding mass. You also need optical systems that remain aligned and clean over decades in space, which is difficult. Radio is more robust but slower. Laser is faster but more fragile. You are choosing which failure mode you prefer. And all of this communication infrastructure, antennas, transmitters, power systems, pointing mechanisms, adds mass, which feeds back into the rocket equation and the energy budget. The mission becomes heavier and harder to justify. We have walked through 7 barriers. Each one is formidable. Together, they form a constraint network where every solution to one problem worsens another. So what alternatives exist, and do any of them escape the trap? Let us examine the leading concepts clearly, noting what each solves and, more importantly, what it does not. Start with beamed energy sails. The idea: instead of carrying fuel, the spacecraft deploys a large, lightweight sail, and a powerful laser or microwave beam from the solar system pushes it to high speed. This removes propellant mass from the spacecraft, breaking the rocket equation's exponential penalty for acceleration. The energy source stays home, an array of ground-based or space-based lasers, so the spacecraft can be extremely light, potentially just grams or kilograms. Breakthrough. Starshot, a current proposal, envisions gram-scale probes accelerated to 20% light speed by ground-based lasers. What does this solve? It solves the outbound rocket equation. You no longer carry fuel for acceleration. The spacecraft mass can be tiny, allowing high speeds without impossible fuel ratios. What does it not solve? Braking. A light sail pushed by a laser from Earth has no way to slow down at Proxima Centauri unless you build a second laser array there, which you have not. So you are limited to a flyby mission. You also do not solve dust shielding at 20% light speed. Dust impacts are even more energetic than at 8%, and a gram-scale probe has no room for shielding. You do not solve communication. A tiny probe with minimal power struggles to transmit data back across 4 light years. You do not solve navigation precision or long-duration reliability for the laser array, which must remain operational and pointed accurately for years while the beam accelerates the probe. Beamed sails are promising for fast, lightweight flybys, but they do not enable rendezvous missions or crewed travel. Fusion propulsion is another alternative. If you can achieve controlled fusion, deuterium-tritium or deuterium-helium-3 reactions, you gain exhaust velocities potentially reaching 1 to 3% light speed, far higher than chemical or ion drives. This relaxes the rocket equation significantly. A mass ratio of 4,000 drops to tens or low hundreds, depending on the fusion reaction and engine efficiency. What does this solve? It eases the exponential fuel penalty, making rendezvous missions less absurd in terms of mass ratio. It provides a compact, high-energy density fuel source. What does it not solve? Fusion is not yet controlled reliably on Earth, let alone in a compact spacecraft engine operating for decades. The engineering hurdles, plasma confinement, sustained ignition, conversion of fusion energy to directed thrust, are immense. Even if solved, you still face shielding, navigation, reliability, and communication barriers. Fusion helps with the rocket equation, but does not eliminate the other 6 barriers. Antimatter offers the highest energy density possible, complete conversion of matter to energy via matter-antimatter annihilation. 1 kilogram of antimatter reacting with 1 kilogram of matter yields roughly 9 times 10 to the 16th joules, about 100 times more than fusion. Exhaust velocity could approach significant fractions of light speed. The mass ratio becomes manageable even for high delta-V missions. What does this solve? It nearly breaks the rocket equation for practical payload fractions. What does it not solve? Antimatter production. Current production rates are measured in nanograms per year at facilities like CERN. Producing kilograms would require millions of times more production capacity and energy. Storage is another problem. Antimatter annihilates on contact with normal matter, so it must be magnetically confined in a perfect vacuum, requiring power and fail-safe systems. Antimatter propulsion is theoretically powerful, but practically distant, limited by production infrastructure that does not exist and may not be economically feasible. Generational ships sidestep the speed problem by accepting multi-century travel times. If you travel at 1% light speed, the journey takes over 400 years. You build a massive, self-sustaining habitat, essentially a mobile space station, and populate it with a community large enough to avoid genetic bottlenecks. Multiple generations live, reproduce, and die aboard the ship. What does this solve? It lowers speed requirements, easing energy and shielding demands. You do not need ultra-high delta-V, so the rocket equation becomes less punishing. You have time to perform mid-course corrections and extensive system maintenance. What does it not solve? Closed-loop life support over centuries. No ecosystem has been sustained in isolation for that long. Social stability across generations, ensuring descendants continue the mission, is unproven and risky. Radiation shielding for a large habitat requires enormous mass. Reliability over 4 centuries is even harder than over 50 years. You trade speed barriers for biological and social barriers. The physics becomes easier, but the systems engineering becomes a different kind of impossible. Mini probes versus crewed missions. The term impossible mostly applies to large, fast, propulsive rendezvous missions, especially crewed ones. A small robotic flyby probe using beamed propulsion or advanced ion drives might be achievable within a few generations of technology development. It would gather limited data during a brief flyby, but it would prove the concept. A crewed rendezvous mission, requiring life support, large payload, braking, and return capability, remains far beyond feasibility. The distinction matters. When we say impossible, we mean impossible for the missions people actually want. Crewed exploration, long-term presence, meaningful science return. Fast flybys are hard but potentially doable. Everything else hits the constraint wall. What would change that answer? Let us compress the argument into a single chain, step by step, so the logic is unbreakable. You want to reach Proxima Centauri and stop there. To stop, you must brake, which means you need propellant for deceleration as well as acceleration. The rocket equation says your mass ratio grows exponentially with delta V divided by exhaust velocity. To achieve interstellar delta V with realistic exhaust velocities, the mass ratio becomes thousands or millions. That means you must carry enormous fuel mass relative to payload. Carrying that fuel mass requires energy to accelerate it. Energy demands grow quadratically with speed, and you want high speed to shorten travel time. The energy required, even with perfect engine efficiency, exceeds current or foreseeable industrial capacity by orders of magnitude. Now add the interstellar medium. High speed turns dust into projectiles. Shielding is necessary, but shielding adds mass, which worsens the rocket equation, which demands more fuel, which requires more energy. Every ton of shielding must be accelerated and decelerated, doubling the fuel cost through the braking requirement. Navigation precision is essential, but mid-course corrections require propellant, which counts against your fuel budget, which was already stretched by the rocket equation. Long-duration reliability means redundancy, which means more mass. Communication requires power and pointing, which require structure and systems, which add more mass. Notice the loop. Every solution to one barrier increases the mass, which feeds into the rocket equation, which demands more energy, which requires more fuel or larger external infrastructure. Relativity tightens the noose as speed increases. Approaching significant fractions of light speed makes every additional increment of velocity disproportionately expensive in energy. You cannot accelerate indefinitely. The speed limit is real, and it ensures that even if you solve the rocket equation with advanced propulsion, you cannot brute force your way to arbitrarily high speeds. You hit diminishing returns. Here is the unifying metaphor. Every solution taxes the same budget in a different currency. You can pay in propellant mass or structural mass or time or energy or risk. But the total cost, measured in the sum of all those currencies, exceeds what we can afford with anything resembling current or near-future capabilities. What would be required to change the answer? You need one or more of the following. External energy infrastructure. Build massive laser or microwave arrays in the solar system to beam energy to the spacecraft, removing the need to carry fuel for acceleration. This helps with outbound acceleration but does nothing for braking unless you build a second array at Proxima, which requires an earlier mission to construct it. A bootstrapping problem. You need new materials with strength-to-weight ratios far beyond current composites, allowing lighter structures and shielding without sacrificing protection. This eases the mass budget but does not eliminate it. You need new mission architecture. Accept flyby-only missions, or multi-century generational ships, or staged infrastructure where early missions establish fuel depots or laser stations, enabling later missions. Each architecture shifts the problem but does not erase it. You need breakthrough physics that we do not currently understand. Warp drives, wormholes, reactionless drives. None of these are supported by known physics, and invoking them is speculation, not engineering. The barriers we have discussed are based on conservation of momentum, conservation of energy, and relativity. These are not engineering limits. They are physical laws tested to extraordinary precision. Perfect rockets means perfect engineering within known physics. It does not mean new physics. If you want to escape the constraints, you need either massive infrastructure investment, turning interstellar travel into a civilization-scale project spanning centuries, or new physics that changes the rules entirely. Neither is on the horizon. That is why, even with perfect rockets, reaching Proxima Centauri remains effectively impossible for practical, human timescale missions. Here is the takeaway. The nearest star is not a longer trip. it is a different class of problem. The distance, the energy, the time, the environment, all of them combine to create barriers that do not add, they multiply. You cannot optimize your way around multiplication. You can only change the terms by building infrastructure, accepting radically different mission profiles, or waiting for new physics. The constraints are not arbitrary. They are embedded in the structure of space-time, the conservation laws, and the exponential nature of the rocket equation. Understanding them clearly shows why interstellar travel is not a vehicle upgrade problem. It is a civilization infrastructure problem. Let us make the comparison explicit. So, the difference between achievable and unrealistic is sharp. First, the nearest achievable mission profile. A small robotic flyby probe, mass around 100 grams to 1 kilogram, accelerated to 10 to 20% light speed using beamed laser propulsion from a solar system-based array. The mission goal is a high-speed flyby of Proxima Centauri, gathering images and spectra during a brief encounter window, then transmitting data back to Earth over subsequent years. The propulsion approach is external beaming, avoiding the rocket equation for acceleration. The biggest constraint is dust shielding at high speed, communication power for a tiny probe, and the lack of braking capability, limiting science return to flyby data. What would need to change to make it viable? Construction of a multi-gigawatt laser array, development of ultra-lightweight sails and instruments, and solving navigation precision for a gram-scale probe across interstellar distances. This is hard, expensive, and requires international cooperation, but it is within the bounds of known physics and foreseeable engineering. Now, the still unrealistic profile, a crewed rendezvous mission, mass around 100 to 1,000 tons including habitat, life support, propulsion, and return capability, aiming to reach Proxima Centauri within 50 years, break into orbit, explore for several years and return data or crew to Earth. The propulsion approach is onboard propellant, likely fusion if available, requiring enormous fuel mass due to the rocket equation. The biggest constraints are the exponential fuel penalty for braking, long-duration life support and radiation shielding for crew, reliability over decades, and the energy budget to accelerate and decelerate such a large mass. What would need to change? Breakthroughs in fusion propulsion, antimatter production, or external braking infrastructure like a pre-positioned laser array at Proxima. Also needed, closed-loop life support tested over decades, radiation shielding an order of magnitude better than current technology, and autonomous systems with proven multi-decade reliability. None of these changes are on a plausible near-term timeline. This mission remains effectively impossible with foreseeable technology. Interstellar travel is an infrastructure civilization project, not a vehicle upgrade. If you want to reach other stars, you do not build a better rocket. You build laser arrays spanning continents, orbital power stations, automated factories in the asteroid belt, and multi-generational planning frameworks. You accept timelines measured in centuries. You design for failure and redundancy at scales we have never attempted. Or you accept that some destinations are beyond reach, at least for now, and focus on what is achievable, exploring our solar system thoroughly, understanding our own star's environment, and perhaps sending tiny, fast, one-way scouts to neighboring stars as proof of concept. Those scouts would return data long after their builders have died, messages from the edge of the possible. Here is the final forward pull. If reaching the nearest star is this hard, what does that imply for visiting many stars or for anyone else visiting us? The galaxy contains hundreds of billions of stars. If interstellar travel is a civilizational infrastructure challenge, not a technology threshold, then the night sky's silence might not mean we are alone. It might mean the stars are farther apart than ambition can easily cross, even for civilizations far older than ours. Or it might mean that the ones who do cross the gap do so slowly, quietly, with patience measured in millennia. Either way, the barriers are real. The distance is real, and perfect rockets, however perfect, still cannot pay a bill written in the currency of light years.